In this example, there is a conducting square that has dimensions L and W that's moving with a constant speed v as it enters and then later leaves a region where there's a uniform magnetic field of strength B. The resistance of the conducting square is R, and I'd like to find the magnitude and direction of the current that flows in the loop at each of these three locations. We'll start by looking at location number 1, where the conducting square is starting to enter the region where the magnetic field is. At location number 1, if there was an electron here in this conducting square, in what direction would it feel a force? The velocity of that electron is to the right because the velocity of the conducting square is to the right. So if we take our right hand and we point our fingers in the direction of the electron's velocity to the right, and then we curl our fingers into the screen due to the direction of the magnetic field, our thumb will point toward the top of the screen. And so a positive charge would feel a force toward the top of the screen, toward point C, but the electron would feel a force in the opposite direction toward point D. And so electrons will start to be sent toward point D due to the interaction between it being a moving charge in the direction of the magnetic field, and by consequence then up toward point C there will be an excess of positive charge. Due to this separation of charge, there's going to be an electric field, an electric potential difference between point C and point D due to that separation of charge. And while clearly now the magnetic field is exerting a downward force on the electron, which I'll draw, and I'll label that FB, due to the separation of charge, positive at the top, negative at the bottom, there is going to be an electric field that exists between point C and D as well. That separation of charge, which causes that electric field, would exert an upward electric force on the electron. The electric force points upwards because the direction of the electric field between points C and D should point in a direction that a positive charge would feel a force. And imagine placing a positive charge at point C or near point C. It would be repelled by the other positive charges and feel a downward force. And so the electric field along the segment CD is directed downward because the electric field points in a direction that a positive charge would feel a force. By consequence then, a negative charge would feel an upwards force, and that's that force vector Fe, the force from the electric field that I'm drawing on the electron. And so as the charges separate at points C and D and that electric field gets created, eventually the electric field will be strong enough that the electric force and the magnetic force that are exerted on that electron will be equal to one another. And the moment that happens, the charge no longer flows, but at points C and D, there is an established potential difference that exists across those 2 points. As long as that conducting square continues to move with its velocity v, then there's going to be a potential difference across points C and D. And like a battery, that potential difference across those 2 points will drive a current through the entirety of the conducting square. So across point CD, we have now a voltage that depends on the strength of the magnetic field, the velocity, and the length of that conductor. And so a good question would be, what would be an expression for the magnitude of the current at location 1? The current would be given by Ohm's law, which is the voltage, which is here the voltage across points C and D, divided by the resistance. I've defined the resistance of the conducting square as being R, and we know that that voltage is given by BVL, where L is the length of the conducting material between point C and D, V is the velocity of the conducting square, and B is the strength of the magnetic field. So if you wanted to know the magnitude of the current, you would have to use this equation to figure that out. If you also wanted to know the direction of the current, you could just imagine being a positive charge at various places around the loop. So if I was a positive charge between points B and C, then I would be repelled by the positive charge near point C and move in this direction. If I were a positive charge between points A and D, I would be attracted to the negative terminal at point D. And so for that reason, at location number 1, the current will be in a counterclockwise direction. Okay. I'd like to take a second now and talk about why I focused on segment CD and not the other 3 segments of the wire. For starters, segment AB is not yet in the magnetic field, and so for that reason the charges in segment AB can't feel a force from the magnetic field. Segments BC and AD are clearly oriented in a way that's different from CD, and so what's happening there? If you think about the electrons in those 2 shorter segments, they still would feel a downward force. But there's not going to be a potential difference that can be created between points B and C due to electrons being deflected downward or positive charge being deflected upward. And so for that reason, what I'll recommend is that anytime you're asked to do a problem similar to this, is just imagine an electron in each segment of the wire, and given the direction of the velocity and the direction of the magnetic field, figure out if the charges are being deflected toward the corners of that segment of conducting material. And the only segment for which that's true in location number 1 is segment CD. I'd like to jump over to location number 3 now, where now that we've spent some time developing everything that happens in location number 1, we can go a little bit faster through location number 3 because something very similar is happening. At location number 3, segment CD is now outside the magnetic field. Segments BC and AD still will not be able to have a voltage across them, but segment AB is still in the magnetic field and now can have a voltage across those 2 points. And so this voltage will be produced, and electrons in this segment of the wire will feel forces in the same kind of way that they felt forces in segment CD at location number 1. If we use the right-hand rule, the velocity and direction of the magnetic field still tells us that negative charge will be deflected downward and positive charge will be deflected upward. We will still get an electric field that has the same orientation as location number 1. And by consequence then, not only will we have the downward magnetic force, but also the upward electric force. And we would get the same kind of separation of charge across points A and B, which would have a voltage delta V AB. The magnitude of this current at location number 3 is going to be the same as the magnitude of the current at location number 1. So the current will still be given by BVL divided by R. So long as the velocity of this conducting square is constant and the length AB is the same as the length CD, then the current will be the same. But the direction of the current, if we imagine being a positive charge between points A and D, that positive charge is still attracted to the negative terminal, but now because of the orientation of the conducting square, that is to the left, and a positive charge at the top between points B and C would be repelled by the positive terminal of that charge separation and be moving to the right. And so for that reason, at location number 3, the current would be in a clockwise direction. So everything is the same at locations number 1 and 3 except for the direction of the current. And so at location number 1 we have a counterclockwise current, and at location number 3 we have a clockwise current. But not just at those locations, but due to segment CD, while it is in the magnetic field, it has a tendency to create a counterclockwise current. And due to segment AB, it has a tendency, due to the geometry of the problem, to create a clockwise current. And so what will happen when both of those segments are inside the magnetic field? Well, CD wants to create that counterclockwise current, and a counterclockwise current between segment CD at location number 2 would look like this. So there's the current due to segment CD. And then segment BC will create a clockwise current, which between those 2 points would be directed like this. And since both of those currents are trying to point in opposite directions, and because they're equal in magnitude, then they'll tend to oppose one another. And so at location number 2, the currents don't add. Because they point in opposite directions, they actually subtract, and the current at location number 2 is equal to 0. So if we were to send this conducting square across the magnetic field in this kind of fashion, at location number 1, the current will be flowing in one direction. Once the whole conducting square gets within the magnetic field, the current would stop. And then as it's leaving the magnetic field, the current would have the same magnitude, but due to the switch in polarity, it would be in the opposite direction. What's interesting about this problem is we can also use Faraday's law and Lenz's law to understand this problem as well, and instead abandon this idea of motional EMF. Faraday's law says that if there is a changing magnetic flux, so delta phi b divided by delta t, that is the rate of change in the magnetic flux, Faraday's law says that an EMF will be produced across a material where there's a changing magnetic flux. And Lenz's law tells us that the direction of the current that is produced by this electromotive force will be in a direction such that the current flows to create a magnetic field that opposes the change in the flux. And so how can we use Faraday's law and Lenz's law to describe the current through this loop at these 3 locations? For this second part, I'm actually going to work backwards. At location number 2, which might have been the most difficult to understand using the technique I was using above, using Faraday's law and Lenz's law, it's actually quite easy to understand. At location number 2, the entire conducting square is inside the magnetic field. Because the entire thing is inside the magnetic field, the flux through the center of this conducting square is not changing. Since this entire region is a uniform magnetic field, there's a constant magnetic flux coming off of that. So the moment the entire conducting square gets inside the magnetic field, the flux through the loop is not changing. And if the flux through the loop isn't changing, then there's no EMF produced. And if there's no EMF produced, then there's no current. And now let's go back and look at locations number 1 and 3, so that way we can see what's happening there as well to get the right direction. At location number 1, the magnetic field B is directed into the screen, away from us, right? If B is directed into the screen and the velocity of the square is to the right, then that means as it moves, more and more flux is going to be going through that conducting square. And so if the flux is increasing, then the flux needs to point in the same direction as B. And so the change in the flux, delta phi b, also points into the screen. And as given by Lenz's law, the current will flow in a direction that produces a magnetic field, an induced magnetic field, that opposes the direction of the change in the flux. So most importantly, the induced magnetic field, B induced, will have a direction that opposes delta phi. And so if delta phi is pointing into the screen, then the induced magnetic field needs to point out of the screen. And if we know now the direction of the induced magnetic field, that's the magnetic field that's being generated by the conducting loop. And so if we know the direction of that induced magnetic field, in what direction is the current? We're kind of using one of our right-hand rules and working backward. So if I have a wire in the bottom left-hand corner here, which has a current going to the right, what will the magnetic field look like around that wire? Well, if I point my thumb in the direction of the wire and I curl my fingers around that wire, I find that above the wire, my fingers are coming toward me, and so the magnetic field is out of the screen. And below the wire, my fingers will be curling into the screen. And so this tells me where the magnetic field is. And if you remember, these are concentric circles which are coming at us and away from us, going in a circular fashion around that wire. So if that's how the magnetic field direction and the current are related for a straight wire like that, then how can we take that and apply it to segment CD for location number 1? So what I want you to do is I want you to let your thumb and going all the way down to like your wrist, and let that kind of be the segment of wire CD, and ask yourself in which orientation of your hand, either your palm facing you or away from you, in which way do we get an induced magnetic field that's coming out of the screen? And your answer should be, when your palm is facing you, your thumb is pointing from D up to C, and your fingers curl out of the screen toward you. And if you were to take your hand and follow that around, going around the entire loop, going from point C to point B, you would find that continually your fingers, which are inside the loop, are pointing toward you out of the screen, and your thumb is moving around the loop at location number 1 in a counterclockwise direction. And so we can follow this line of thinking all the way through to get a current that is counterclockwise. And I know that it's counterclockwise because I know the direction of the induced magnetic field. That induced magnetic field in that conducting loop is due to the change in the flux, which is described by Faraday's law and Lenz's law. So the last thing we need to do now is look at location number 3 and figure out if we can do the same sort of thing for location number 3. At location number 3, the direction of the magnetic field is the same, right? B is directed into the screen. However, at location number 3, the conducting square is leaving the magnetic field, and so for that reason, the flux through the inside of the conducting loop is decreasing. And if it's decreasing, that means that delta phi B needs to point in the direction opposite of B. And so delta phi B is pointed out of the screen. And if delta phi B points out of the screen, and the induced magnetic field needs to point in a direction that opposes the change in the magnetic flux, then that means B induced needs to point into the screen. Okay. So now we need to do the same thing. I need the direction of the current to be in such a way that when I use my right hand rule, my thumb points in the direction of the current, and my fingers are pointing in the direction of the magnetic field. At location number 3, that means my fingers need to be curling into the screen while they're on the inside of the loop. And so between points A and B, if you orient your thumb from A pointing to B, then your fingers will be curling in while they're inside the loop. And as you curl your hand around point B and point C, your fingers will continually point inside of that loop, and your thumb will guide you around the loop in a clockwise direction for the current. So the current is clockwise. Understanding Lenz's law, Faraday's law, and motional EMF are incredibly important for understanding how electricity and magnetism are related to one another. So I really hope that you're able to follow all of these steps in order to analyze different problems, and not only use motional EMF to get the equation for the magnitude of the current, but have multiple routes for determining the direction of the current based off of your understanding of these laws that we're talking about here.